things. In this one, we will talk about how to find the distance between skew lines like this in 3D space. So if we have skew lines, let's say in this example we use L1, L2, and they have some points that they both go through. Namely, this is vector notation for the lines. It means we have a point for each of the lines that it definitely goes through, and then some parameterizing component A or B here. Or it can also, it's often written with some Greek letters, for example, but I chose for simplicity, namely A and B, that multiplies this second column, which is a vector that gives each of the lines its direction. So the point here is we have line 1 and line 2, and the way they are defined both is they go through a point, and then they have this direction vector, namely for L1 is direction 3, 2, 4, 3 in X, 2 in Y, 4 in Z. For the line 2 is direction 7, 2, 0, 7 in X, 2 in Y, and 0 in Z. And our question is how to find when we have them in 3D space, meaning something like we have 3D space, and these two lines are somehow not intersecting, but they're also not parallel to each other, and so on. What is their minimum distance? What is the distance between these two lines in space? So to answer this question, there is more methods to actually approach it. We can use some methods involving projection and so on, and some more, let's say we can even, for example, use cross product and so on. But in this case, I will try to approach it from a perspective that we can, first of all, view these lines, any point on both of these lines as a parameterized vector from the origin to any point on that line. Second of all, I will create a new vector that will generalize the distance between these two lines. And then, using the property that dot product between two things equaling 0 means these two things, namely vectors, are perpendicular. Using that, we'll create two equations which will together have in total two unknowns. And solving that will give us basically an answer for A and B in the end, in whatever context we will actually create in a second, and then we will plug it back into a particular equation, and it will give the distance. So our goal here is to find the minimal distance between these two lines. They're skew and they're both in 3D space. So first of all, it's useful to realize that we can also say that if there's some point capital A on L1, it can be written like this, that X will be the X element of the point, the line 1 definitely goes through, and the X coordinate of the direction vector times A. So any X will be 0 plus 3A, any Y will be 3 plus 2A, and any Z will be 2 plus 4A. Now, this is very useful. The same thing we can do for L2, so we can say that any point B on L2 will satisfy that it can be given that its X component is 5 plus 7B. Notice we don't have A and B same, they're different letters to emphasize that, and it's important to keep them different. 4 plus 2B is any Y, and any Z will be 1 plus 0B. And now if we want to create some general vector AB, basically that will mean we will have some, in general, some vector AB. What that will mean is we subtract these two general things from each other and put that as, again, free entries of a single free entry vector. So what we can do is subtract what B is from A, and that gives 3A, and just subtract the like components. So 3A minus 5 minus 7B. For the X component of AB, then the Y will be 3 plus 2A, 3 plus 2A, minus 4 minus 2B, and the Z will be 2 plus 4A minus 1. So that's 1 plus 4A. And this can be simplified, so 3A minus 7B minus 5, that's not too simplified anymore, but this one is. So it's 2A minus 2B minus 1, and this one again is sorted out already. And now we will use this. This is basically our main vector that we finally created. It's like an abstractized version. So basically we created some general parameterization for any point on L1, general parameterization for any point on L2. Those were the A and B. And then we do the general parameterized vector between these two. And that is this AB. And it's in terms of A and in terms of B. And what we want now is the minimal distance between the lines. And it means we want to create a vector, A and B, where A is on line 1, B is on line 2, such that this vector is perpendicular to both of these. That will generate the minimum, that will generate the particle vector that signifies the minimum distance between the lines. So we want this vector to be perpendicular to both this vector and this vector. How we do that? Well, we can take it and put it in dot product with this, and that should equal 0. Also, we take this, then put it again in dot product with this one as well, with the direction vector also of L2, not just L1, that we do first, and L2. And that will generate two equations, two linear equations involving A, B both. So what do we get? Well, AB must be perpendicular to this, and AB must be perpendicular to this. So I dot product this result right here, 3A minus 7B minus 5, 2A minus 2B minus 1, and 4A plus 1. And I dot product it with 3, 2, 4. So again, we want this vector to be perpendicular to this general AB that we created. And how is it going to be? It's going to be equal to 0. And now we can do the dot product. And it will generate a two-variable equation involving A and B. So 9A minus 21B minus 15 plus 4A and it continues. Equals 0. And also, we have to do this another time, but with the other vector. So this was for the first vector, and now we do this another time, but for the vector of L2 as well. So we now dot product the same thing, but with 7 to 0. So that has to equal to 0, and that will be and then this is 0, so this doesn't even have any effect. And now both of these basically got two linear equations, and we can simplify them. I'll do it in the way that I said this equals 0, and on the other side I will just simplify this thing. I will just write once again this, but I will simplify it. So just to make it clear, this is one linear equation we now have, and this is the other one. And these two we'll now use to gain A and B. So to simplify this further, 9A plus 4A plus 60A, 29A, namely, 4A, 13A, then these, minus 21, minus 25, minus 15, minus 17, minus 13. So this is our first equation to take. This can be simplified also. So this is 0 must equal 21A, 25A, minus 53B, minus 37. So 25A minus 53b minus 37. So this is the second equation to take into account. And now, after these dot products, we have just two equations. So at the end, just to quickly skip through a bit and show where this is going, we will then just take the magnitude of AB, and that will be the distance, the minimal distance between the lines. The magnitude of AB will be taken. That is the goal right now. So what do? We further continue with this idea, and basically we now solve this system of two linear equations. Now this is not necessarily going to have nice results or ones to calculate by hand, but we can at least attempt to do something. So we can say things like 29a will equal 25b plus 13. I'll give a little hint, like a general solution to this, but again, finishing this might be far more practical with a calculator at this point. So a will be this in terms of b, then I plug it in into the second equation. So it's gonna be minus 53b minus 37. Now we solve for b. B will be something, alright? So we solve for b, we solve for a, and after all of that, to get the distance, what we will do is basically we go and refer back to AB. So we go and refer back to AB, which what we do is this basically. The distance between the lines will be the magnitude of this vector. We generalize it here in terms of a and b. But from these two equations, just finish solving them as a system of two linear equations of two unknown in total. There will be a numerical result for both a and b. Then plug this into this vector, and it will give three enumerated, that can be low fractions inside there or something, three enumerated entries. And then simply we do the magnitude of it, which will be in general this. Basically, this is kind of a general thing before we evaluate the a and b. And the enumerated result of this will be the distance between the two lines. But of course, a and b you will plug in into here, where you can, and so the result will also not be in terms of a and b, but it will be actually concretely enumerated.